In this video, I will show you how AI can make robotics more accessible to the general public in two ways by presenting the project we submitted for the last two Mistral hackathons. Robotics today is not yet widely adopted by the general public. I like to compare them to early computers in the 90s, which lacked intuitive user interfaces and were difficult for non-experts to use until Apple and Microsoft came along and transformed them into powerful, easy-to-use daily devices. For robotics to see a similar transition, two challenges must be overcome to make them accessible for the general public. First, an intuitive way to gain insights from sensor data must be created. I like to bring the example of a drone flying over an agricultural crop while recording a video. Is there a way how we can extract meaningful information out of the data without having to manually go through the video? The second challenge is to enable an intuitive way to control robots. For anyone who has controlled robotic arms before, know how much practice it takes to steer them remotely with a joystick. And moreover, it requires extensive programming knowledge in order to program them to do some tasks autonomously. So for them to be more accessible for the general public, for example, as a flexible companion in the household or as an extra helper in retail, this initial entry burden needs to be stripped off. Let's begin our dive into the first topic of gaining insights from sensor data. And as many of you might guessed it, the solution here is to leverage on the contextual understanding of LLMs. By feeding an LLM the right sensor data from your robot, like a stream of camera images, you can start asking questions about it and receive very concise answers. As examples, you can ask questions about your harvest or if anything suspicious can be found nearby with data coming from a camera mounted on an arm or a mobile platform roaming a premise autonomously. During the Mistral hackathon in Paris earlier this year, we set out to achieve exactly this. We created a pipeline to query a video we hand recorded on site. Since Mistral's LLM can currently process only text, our first step was to use a captioning model to generate textual summaries from the video. Specifically, we generated contextual summaries for each frame and stored them in a database. Once the database was filled up, we used a RAG approach to query and analyze the data. One weakness of these captioning models is that they often only provide high-level qualitative descriptions and leave out quantitative details, such as the exact number of people in a frame. To address this, we use a visual segmentation model on the retrieved frames to draw bounding boxes around objects, which provides extra meta information for the LLM to formulate a concise answer. Now, such a pipeline consisting of open source and relatively small models loosely coupled to each other can now be deployed for robotics as well. Imagine now that your data feed stems not from a video, but instead from raw sensor measurements. In the example above, I'm showing you a mobile manipulator with some autonomy payload developed by the company Autodiscovery. The robot has a nitrogen sensor attached to its end effector, and the robot is tasked to drive across the field autonomously and take samples off the ground. Nitrogen level is very important here since it indicates how much fertilizer a crop area requires. Following the same approach of capturing and segmenting the data, you can now query the system about your crop health. Upon question of it field need more fertilizer, for example, the system can respond with that only 5% of the entire area need fertilizer. And this would save a farmer enormous amount of money as fertilizer is expensive and you only want to apply it where it is needed. Now this summarizes intuitively gaining insights from sensor data. Let's now switch gears and ask ourselves if we can improve current manual robot control and make it more intuitive. And the answer is again yes. We can leverage on the real world and common sense understanding of LLM to enable intuitive control of robots given a user commands. I show you here a couple of examples where you can task two manipulators to make you a tea or command a humanoid to sort things out for you. I find the last examples most interesting. Imagine tasking a robot not with a direct command, but with something more general, like to find specific room in a building. It will then go through an exploration process where it has to solve mini tasks on its way, such as figuring out where it is, opening doors, or finding the correct room using visual sensors. Now, there are multiple ways to solve this task, and one method is explained in a paper by Imperial College London named language models as zero-shot trajectory generators. Now, those are very fancy words, but in simple terms, it means that an LLM who has access to the basic skills of a robotic arm can determine the correct order of the skills in order to accomplish a task. For the simulation robot on the right, the skills are defined as follows. It can detect an object and return its coordinates. It can open and close or rotate the gripper. It can move the gripper to a certain position, lower it, and lift it back to its starting position. Now, those skills define the entire physical capability of the robot. And if you provide these to the LLM, it can figure out an order in which most sense to fulfill a task. It's almost like if you give the joystick of the robot to the LLM and let it control the robot. Now, the authors have demonstrated this capability with GPT-4 and other LLMs with higher parameter count. When it comes to task completion, GPT-4 performs the best with 75% success rate out of the box. However, for use cases secured environment, deploying an application where it sends your data to unknown servers is not a good idea. Preferably, you want to deploy a small model on board to eliminate inference delay for it to work without access to the internet. So this is exactly what we did for the online Mistral hackathon. Given a user command, for example, pick up the bottle, Mistral 7b first figured out that it needs to call the detect object function, which uses visual segmentation to figure out the exact location of that bottle in the real world. This information is then fed back to the LLM, which subsequently generate a trajectory code output made out of these basic skill functions as defined previously. This is then fed to the controller, which moves the robot according to the predefined trajectory. So where does fine-tuning come in? Now, the base Mistral model initially had a lot of problem generating the correct trajectory, as can be seen in the following video. So in the video, you can see what happens when the Mistral LLM generate executable code which makes no sense. Most of the time, however, the base model was not able to generate executable code in the first place. So what we thought is, can we fine-tune Mistral with data coming from GPT-4? As the authors of the paper used GPT-4 with great success, they were kind enough to provide us with a dataset of their runs. One of the dataset is provided here, and you can imagine this as a conversation between an LLM and a user. First, you have a user prompt commanding the LLM to accomplish a task step by step. The initial expected LLM output would be to call the detect object function first. The coordinate output of the segmentation model is then fed back as a user prompt to the LLM, which finally generates the code output made out of basic skills in the correct order. The final system performs more robustly, but is not yet perfect. Here we showcase an example of the robot task with moving a box to the left. Motion-wise, it correctly understood the task. However, it failed to hover over the box first to grab it perfectly. Here an argument can be made that with more training data, this problem would be mitigated. Or alternatively, if we switch to the recent largest model Mistral has released, we hypothesize that this type of trajectory planning can be accomplished with greater success. Nonetheless, we demonstrated that a small LLM can be deployed on board and is capable of solving such flexible tasks, which enables intuitive control of robots. In this mock example here, the system is deployed on a small mobile manipulator. If you can combine such a system with voice command, you all of a sudden have a robot companion in your household that can help you with automating physical tasks. This is all something we are currently actively working on, deploying their software on a real robot. This is how my kitchen currently looks like, and I will soon release a video of its development from scratch, so make sure you like and subscribe. And this concludes the video on how to overcome the challenges of robotics nowadays in order to make them more accessible for the general public.